Hi everyone and welcome. In this video I would like to go over again something that I went a little bit too fast over in the lecture of week 8. And I'm talking about these problems where we have to test whether the efficiency of the vaccine is 50%. So let's get back to where we were. And to start, we're going to remember exactly what we were doing. There were two approaches to solving the problem. The first was to use a sampling based on zeros and ones. And if you remember, what we're doing is to create first a cohort that would be based on 0, 0, 1, where the zeros here mean people who did not receive the vaccine and the ones were people who received the vaccine. Because you remember, there were twice as many people who did not receive the vaccine compared to the people who did. And because there are more than just 3 people, we say that we want 154 repeats of that. So that's the cohort here. It looked like this. And from this, we were able to sample a group of people, 108 people in total. So that would typically look like this. When we count the number of people who got the vaccine, we just compute the sum here, and that would look like 38 here, 34, etc. We could resample the number of people who got the vaccine among the people who got COVID-19. So getting the null distribution in that case where the efficiency was assumed to be 0% in the null hypothesis was, as usual, using replicate here with, for example, 1,000. And when we did this, we could quickly just get the null hypothesis in that case. And remember that quite simply, we could get the histogram here that looked typically like that. Now, when we moved on to the final question of problem 1, for instance, we had to test whether the efficiency was 50%. And the way we proposed to do this was to create a vector that we call bias, and that be putting the values 1, 1, and 0.5 here. So we give a weight of 1 for the people who have not received the vaccine, and a weight of 0.5, like half, for people who have received the vaccine. And that is the definition of a 50% vaccine efficiency. And we need to create a vector which has the same length as the cohort. That's why we repeat that 154 times. And now when we get the null distribution, actually when we get the samples, we say prob equals bias here. And you can see that it puts much fewer 1 than before. When we compute the sum, we get much fewer. We get about 1/2 fewer ones. So that's really one way that we can model the idea that the efficiency is 50%. And to finish the problem, we just said that here we need to say prob equals bias. And when we now represent the histogram of the null distribution, you can see that this is shifted to the left. The numbers are lower, of course. And finally, because we want a statistical test, we said that one way to finalize the problem is to say that we put a threshold here at the position 0.05. And that threshold was 70. So that's the first way to solve the problem, and there's really nothing wrong with it. This is a way which, in my opinion, is the most straightforward and the most accurate. But there was another way where we can use the binomial distribution. And if you remember, the way that we can use the binomial distribution is, of course, with the function or binom. And if we want to sample just one binomial random number, we say that the size is 108 and the prob is equal to 1/3. So that here gives us a binomial random sample in the case that we assume that the efficiency is 0%, not 50%. And it's a little bit simpler to produce a null distribution in that case, because all we have to do is to set the parameter n here to 1,000. And so that gives us the null distribution. And now came the question, how do we transform that if we want to account for the fact that the efficiency of the vaccine is 50%. And it was suggested that we take this 1/3 and we divide it by 2. So we take the number of people who get COVID-19 and we divide it by 2 if the vaccine has a 50% efficiency. And so when we do this here, and we compute the new threshold, we see that this is 12, which is kind of far from 17. And I went a little bit too fast over what is the difference between these two settings, and I'd like to explain that a little bit better now. So there are two things that we need to modify in order for these two methods to agree. The first is that, remember, the binomial distribution corresponds to a sampling with replacements. The fact that we have chosen one person doesn't change the probability that we choose that person again in the case of the binomial distribution. So the equivalent, if we're using the previous method, is to here say replace equals true. The default when we use sample is to not replace one particular element. So if we want to have something that corresponds to the binomial distribution, we have to change that to replace equals true. So when we do this, now do the two methods match with each other? Let's check that. Not quite. We went from 17 to 15, but this is not exactly the same as what we had with the binomial distribution, which is a threshold of 12. So what is happening? What's happening is that in reality, if we say that the efficiency of the vaccine is 50%, we shrink by a factor 50% the number of people who get COVID-19 that are vaccinated, then here it should not be 1/6, it has to be 1/5. So when we do that, we could see that the binomial distribution method here and the sample method give the same sample, the same threshold, which is 15. Okay, so that is the threshold when you assume that you can resample people multiple times, so that's adjusting for replace equals true, and there is this a little bit weird and surprising probability of 1/5, which actually corresponds to what we have done with the bias that was 110.5. So I'd like to explain why there is a probability of 1/5 here. Let's go over to the whiteboard in order to explain that a little bit better. So here, what we have to think about is that the sample has got approximately 1/3 of the people here, actually exactly 1/3, who have received the vaccine. And there are twice as many people who have not received the vaccine. So we're making potatoes, and this one is approximately twice as big as this one. Well, that's what I hope it is. Then we say that among the people who have not got the vaccine here, there is a proportion X of people who get the disease. If we now look at the proportion with the vaccine, so that proportion X should be here, but what there is actually smaller. This is X divided by 2. And that's what we mean when we say that the efficiency of the vaccine is 50%. We say that the proportion here that we get in this smaller sample of people who have gotten the vaccine is just half of the proportion in the bigger sample. So now let's count how many people got the disease. So that's X divided by 2 plus, because here you have a size of 1 and here you have a size of 2, that is 2x. Okay, you see that here the potato is twice the size, so you got 2x. So that's the total number of people who get COVID-19 here. And now, among them, what is the proportion of people who got the vaccine? This is x divided by 2. And so if we compute that, we simplify by x, we have 1/2 in the numerator. In the denominator, we have 1/2 plus 2. And now when we multiply everything by 2, we see that this is 1/5. So this is where this 1/5 is coming from, is that if you divide the size here of that population by a factor 2, you shrink it by a factor 2, then the total number of people who do get COVID-19 and who have the vaccine, so that's the number of ones in your sample, is 1/5. So this is where this is coming from here. That's a little bit of a detail, but that's one of the reasons why I don't really like this definition of the efficiency of a vaccine. It makes it not very intuitive. Like in that case, everybody expects it should be 1/6, but it's actually 1/5. So that point is not very, very important, because that has to do with the definition of vaccine efficiency, etc. But this is not intellectually a very, very deep point. More of an issue is something else that I did not mention, and that is actually quite important to describe now while I'm at it, is that if you remember, so we have here the distribution of the statistic under the null hypothesis that the efficiency is 0%. When we say that the efficiency is 0%, we are saying that the vaccine is as efficient as the placebo, or as efficient as no vaccination at all. And we had a case where the threshold was actually on around here, and the observed value as well. And in the case that I gave on Tuesday, I said that we rejected the null hypothesis, but that happened only when we took a threshold at 5%. If we set the threshold at 1%, we would accept the null hypothesis. So let's take that setting where we accept the null hypothesis because we have a threshold of 1%. So we say, okay, fine, in the first questions of the exam, we'd say we accept the null hypothesis that the vaccine is not efficient. Fine. But then what happens? We're doing another question, and this time we're testing whether the efficiency is 50%. And remember, the efficiency of 50% shifts the distribution of the null distribution to the left. I'm going to change color, actually, put it, for example, in blue like that. So once we have made the new assumption here, the distribution looks something like that. So in this particular case with the black curve, we have said that we accept the null hypothesis at 1%, but look at this curve, which is here, which is shifted to the left, which means that this is now closer to the observed value, which is in red. Well, we also accept the null hypothesis, and this is something that is extremely weird. We have accepted two null hypotheses which are completely incompatible. So if that shocks you, then this is because you're paying attention. This is very shocking, and this is something that is, in a sense, normal for statistical tests, but that is still, in many people's mind, a weakness. And that weakness is the fact that when you accept a null hypothesis, you do not accept it at the exclusion of other hypotheses. This is not the only hypothesis that you accept. And that's something that is really, really important to understand in the context of statistical tests. Just because you have accepted one null hypothesis doesn't mean that you have excluded others. I know this is really weird. So in that particular case, you could see that we would, at the threshold of 1%, accept the null hypothesis when the distribution is like this, but we would also accept the null hypothesis when the distribution is like that. So what's the point, and how can we make peace with that very strange phenomenon here? So one way to make peace with it is to say that you never really accept the null hypothesis. You just fail to reject it. So now when you consider that particular case, you could say we failed to reject this null hypothesis. We don't have enough evidence to really reject it, but we also fail to reject the null hypothesis. So we can't say that this is false, and we also can't say that this is false. That's one way to think about it. So now the fact that they're not that they are mutually exclusive is less of a problem here. Another way to think about it is that statistical tests are really made to make decisions. They're not made to make estimations. So you have to be clear about this. If what you want is to know the efficiency of the vaccine, then you don't need to make a test. This is the wrong approach. It's not going to tell you the answer. What you need is to make an estimation approach, like for example maximum likelihood estimation or something like that. But you should not make a test. A test is for making a decision, not for estimating the value of a parameter like the efficiency of a vaccine. Right? So this is a bit less shocking to think about the tests as the way that you're going to make a decision, in the sense that you would make a decision when your hypothesis is the black one, or when your hypothesis is the blue one, and you just make the same decision. That's what you're saying by saying that you accept the null hypothesis in both cases. You're not saying anything else than that. So just to recap, when you accept the null hypothesis, this is not at the exclusion of other possible null hypotheses. There are a couple of other hypotheses that are quite close to your null hypothesis that you would equally accept, and that's completely normal in the case of statistical tests, but that's a little bit shocking the first time you see it. That's what I wanted to share with you. Good luck for the quizzes, and see you at the tutorial.